the dissolving of ammonium nitrate is used in chemical cold packs if 28 grams ammonium nitrate is dissolved in 91.7 milliliters of water at 30.1 degrees Celsius. What is the final temperature in degrees Celsius of the solution? So the mass of the solution is the mass of the salt, and our salt here is our ammonium nitrate. Mass of the salt and the water together. Now, this is going to be a coffee cup calorimeter problem, and so I'm going to start abbreviating that as CCC for coffee cup calorimeter. So this is going to be CCC with reaction. Which means that our basis equation is Q reaction equals minus Q solution. And let's see. Okay, so, and in this one, we're asked what's the final temperature, and we're given delta H. So it's sort of like the problem for the one of the previous ones we worked, except we're sort of backwards. We're solving for a different thing. But the process is still the same. For Q reaction, it's going to be delta H reaction times moles reacted. There's still a minus sign in here. And for the solution, because the solution is changing temperature, it's going to be mass of solution times specific heat capacity of the solution times T final minus T initial, where I could add solution to these as well, since it is for the solution. However, there is only one temperature change, so it's the only T sub F and T sub I for this problem. So, and now once we have this, we can go poking around our problem to see what all of these numbers are. I typically start by filling in the numbers for my solution first, and I'm going to move my minus sign over a little bit. So my mass of solution, it says, is the mass of the salt and the water together. I have 28 grams of salt, and I have 91.7 milliliters of water. And for water, 1 gram equals 1 milliliter. So if I have 91.7 milliliters, and then I have 91.7 grams. So 91.7 plus 28 will be the mass of my solution. So 119.7 grams of solution. This particular problem does not say anything about the specific heat capacity of my solution. In the lecture outlines and on the exam, if I don't tell you what to use for a solution for its specific heat, you may use the specific heat capacity of water. And that's because the solution is I would say usually, so it is the solvent water, and so the properties will be similar to water, and we may use it. So now I'm going to put in 4.184 joules per gram degree Celsius, and that number is on your conversion and equation sheet. I don't know T final, but I do know T initial, like so. And do you see my minus sign there? I almost forgot it. Phew. Okay, now I do know my delta H reaction. It's called delta H dissolving here, but that's only because this is a dissolving reaction. If we don't know what kind of reaction it is, I just call it delta H sub Rxn. And you may, but this is our delta H Rxn. You'll note that it's in kilojoules per mole, and that over on the right-hand side, we have a joules per mole. So something has to be changed. Now, I don't know about you, but I prefer joules. And so I'm going to convert everything into joules. To convert from kilojoules to joules, I'm going to move the decimal point 1, 2, 3 places to the right and get 25,700 joules. And the only thing I don't have is my moles. And that's the only thing really for these problems that we know how to do from before, right? The other stuff we're learning right now. We know that we have 28 grams of a substance, and we know how to convert that into moles. Let's go ahead and do it. 28 grams. My molar mass, let's see, 2 nitrogens plus 4 hydrogens plus 3 oxygens. I get 80.05. NO3, there we go. And so 28 divided by 80.05, 0.34978. I'm going to round it to 0.350. Moles. And I can plug this directly in because it has a 1 coefficient. And the only thing that's left is to solve for T final. Now multiplying this all out, I will multiply out this time the left-hand side. 25,700 times 0.350 is 8,995 joules. Oh, I'm sorry. When I did this joules here, it should have been joules per mole. I love my units. I love canceling my units. I'm showing that the moles are canceling here and I'm just left with joules. Don't forget the minus sign. I have these two numbers, and again, I will distribute minus 119.7 times 4.184, 4.184. I get 500.8 for these two multiplied together. Distribute that in this term over here. I get times T sub F. I get a double negative, so my next term will be positive. Oh, 500.8 times 30.1, 15,074. And now I have to bring this 15.074 over to the other side. If I do, I'm going to be subtracting off that, so I should get minus 6,079. Well, I'm just going to drop my units here, as much as I love them. equals minus 500.8 T sub F. And T sub F equals is that right? Let me write it down. 12.1 degrees Celsius. Let's see, 6,079 divided by 500.8. Yeah, okay. 12.1 degrees Celsius. I wasn't sure there because I thought I typed something incorrectly, but oh, there we go. And a couple things I'll note here. So this reaction is endothermic. Endothermic reactions take in energy. And so when a reaction takes in energy, that means that the final temperature of your solution will be lower. If you remember from the previous problem, how many problems ago? 3 problems ago, we had a reaction that was that turned out to be exothermic. Somewhere around here I have my work. That was exothermic, and that was the temperature went up. So let me just make this note. So endothermic reaction. So delta H is positive. Final temperature is lower. Exothermic reaction. Delta H is greater than 0. Final temp is higher. And the reason I make this note is because it is so easy to drop a minus sign in here. So I want you to know what you should expect for an answer. This problem is kind enough to tell you that it's a chemical cold pack. And that is a hint that your final temperature will be lower than 30.1, and so it is. There are other problems in which it involves chemical hot packs, and for chemical hot packs, you would expect your temperature to be higher and involve exothermic reactions. Any questions about this? All right.